Okay, we're going to be wrapping up section 9.3 today, talking about significance tests for population means. And up until this point, we've pretty much been doing all of the steps by hand. There's a couple of the steps that we can replace by executing it on the calculator, although I would recommend that every significance test that you don't always use your calculator. Otherwise, you will not be very familiar with the formula for how to get the T-score, and those sometimes pop up as multiple choice questions, being very comfortable with that formula. So I would just switch it up, sometimes use your calculator, sometimes go ahead and write out the formula for coming up with the T-score and doing T-CDF. But I think that you'll find this feature on the calculator helpful. So I have some screenshots here to kind of show you what you're going to see on your calculator. And that's what this page here is for. And we could reference back to that. I'm also going to pull the calculator out. I guess the big thing that I just want to emphasize with you is if you are in fact going to use the calculator feature and you show no work at all, including like not reporting some of the values that the calculator will report for you, you are definitely going to be docked points on the AP test. So they are still wanting you to name your procedure, one sample t-test or a paired t-test. They're still going to want you to report that t-score, that test statistic, as well as the degrees of freedom and the p-value. Those are all things that if you use the feature I'm going to show you here today on the calculator will give you these values, but you must write them down and report them on your paper, otherwise you will not be given full credit for the problem. Okay, so let's take a look at this next example without running a full, like all the steps for this significance test, which you would generally always be expected to do. Let's go ahead and just look at sort of how the mechanics are on the calculator to run a significance test. In this example, it says a national chain of SAT preparation schools wants to know if using the smartphone app in addition to their regular program would help increase student scores more than using just the regular program. Now, on average, the students in their regular program increase their scores by 128 points during the 3-month class. To investigate using the smartphone app, they have 5,000 students using the app. So that's our sample size, 5,000 students who are using the app with the regular program, and they measure their improvement. Okay? Then they're going to test the following hypotheses. So we know that it says on average, the students in their regular program increase their scores by 128 points during the 3-month class. So we're going to say that that is what our null hypothesis is, that the average increase is 128 points. We're wanting to know if in addition to this regular program, we also incorporate the smartphone app, if that increase might not be larger than 128. So that's our alternative hypothesis with a greater than symbol. Okay, we are defining mu to be the true mean improvement in SAT scores for the students at this school. After 3 months, the average improvement, this is just from a sample here, X bar, is 130. The standard deviation of that sample, 65. Now it says here, without running all the steps of a significance test, they're asking us to find the p-value. We know that's what we use to compare to our alpha level, and that helps us make our decision whether we're going to reject the null hypothesis or fail to reject it. And then we want to use that conclusion to determine whether we think our results are statistically significant or not. Okay. Now again, traditionally we would work our way through that acronym called PHANTOMS, but right now I just want to show you how you could run this on your calculator. I guess I should mention that when you go through that acronym, the calculator portion is actually only replacing 2 letters in that acronym. It's replacing the letters for T and O in PHANTOMS. The T is when you get the test statistic, the T value, your T-score, and the O is when you obtain the P value. So that is the only 2 steps that the calculator portion would replace here. Okay, so here's what you would do. On your calculator, let me get this pulled up here. Okay, you're going to press the stat button. You're going to bump to the right to the test. This is where we found some of our confidence intervals, t-intervals, things like that. But you're going to come down to option number 2, titled t-test. Okay, t-test. That's what you're going to be choosing, whether it's a one-sample t-test or whether it's a paired t-test. You're choosing this exact same option here. Okay, now it has a couple of choices here. Either you have all the data, which we don't have on this one. If you remember a few examples ago, I think we had a bunch of the data for like the length of 6-inch subs. Like if you have the data set from your sample, you would choose data and then you would make sure that your data was placed in L1. If rather than having the data, you have the stats on that data, meaning you have the average and the standard deviation like we have in this problem, you want to choose stats. Okay, now let me slide this calculator over here. Okay, we need to fill in the blanks here for this. We're going to bump on down and put the value for our null hypothesis. And that is going to be 128. We can see that here in the problem. Okay, the x bar, I highlighted that in blue here, that's 130. Our sample standard deviation, 65. And the number in this sample, there were 5,000 students. Now, the next line, you're going to choose which direction your symbol is for your alternative hypothesis. This one, the alternative hypothesis is a greater than. You can see that's already what is selected here. Okay, so I'm going to come on down to where it says calculate. I'm going to go ahead and press enter, and these are the values that they're going to report for me. Okay, so I'm going to go ahead and write down that 2 places is usually fine. That the t-score is 2.18. The p-value, okay, this would be the shaded area, 0.0148. Okay, so if I were drawing a picture of this, here's my t-curve. I got my t-score over here, 2.18. It said this was a one-sided, it's a greater than, so I'd be shading everything to the right. That p-value represents that area right there. Okay? Okay, now something that it actually doesn't report on the screen, but it is very important that you do this. The graders will be looking when you have identified what the degrees of freedom are. So we would want to report that as 1 less than our sample size, 4,999. And the other things on this calculator screen, I don't think we need to write those down. Those were provided here in the problem. Okay, so we can see that the conclusion that we would draw, and they don't actually name an alpha level here. Okay, so assuming that we just go with the default alpha level of 5%, we would be saying, well, since the p-value of 0.0148 is less than an alpha level of 0.05, we reject the null hypothesis. We would go on to say that we have convincing evidence in favor that the true mean improvement in SAT scores for students at this school is actually greater than 128 points. Now, if my alpha level, though, was 0.01, well, then I would be drawing a totally different conclusion. Okay, I would say something like, well, since the p-value of 0.0148 is greater than an alpha level of 0.01, then I would say we failed to reject the null hypothesis. Okay, I would say that we do not have convincing evidence that the true mean improvement in SAT scores for students at this school is greater than 128. And this is why it is very important prior to running any significance tests. If you're actually doing real research here, you should always set your significance level prior to running your significance test. You never wait till the end and set it. That's considered extremely dishonest and kind of making the numbers fall the way that you would want them to fall because you want the conclusion to be whatever you're looking for there. Okay? So if we went with the 5% significance level, anytime you are rejecting a null hypothesis, that's when we say that the results are statistically significant. So we would say in this scenario, the results are statistically significant. In the other scenario, I would say that they're not statistically significant. Depends on what your alpha level is there. Okay, so we're gonna get a little bit of practice here with using our calculator for this, but that was just a very small intro here just to kind of show you how that works. Here's a good example where they're giving you all the data, okay? They're giving you the raw data from the sample here. This is the level of dissolved oxygen. We're gonna call that DO, dissolved oxygen, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along the stream, and here are the results in milligrams per liter. As you can see, we have the raw data. This is what we'll be wanting to put into L1 here. Let's just walk through these steps of the phantoms process here, and we're going to use our calculator for step T and O. Okay? So we're going to define mu to be the true population mean DO level in the stream or river. Okay. All right, our null hypothesis, it says in order to support aquatic life, it's got to be 5 milligrams per liter. And so it mentions here, anything that's below that puts the aquatic life at risk. So my alternative is going to be less than 5 milligrams per liter. We're going to set an alpha level of 0.05. Okay, we're going to go ahead and proceed here with our assumptions, our conditions. Okay, the first one, random condition. We're just going to cite 15 randomly chosen locations. That was mentioned in the problem. Now, the only time that we don't have to do the 10% condition is if it was an experiment. This was not. We randomly chose these locations. So I'm going to say 10 times 15 is 150, and certainly that is less than or equal to all locations that could have been chosen here. Okay, so that seems reasonable. Okay, and then our final condition is the normal condition. Again, I cannot cite the central limit theorem because my sample size is not 30 or greater. Does not mention that the population shape is normal. So I'm left with constructing a box and whisker plot on my calculator and then transferring that onto my paper. Okay, so here I have already taken the data and I've put the data for this particular problem into L1. I'm going to come up here to stat plot. I'm going to turn on the stat plot, and I want to pick the box plot that has the 2 dots there. That way, if there are in fact any outliers, it'll show them to me as dots extended past the whiskers. I'm going to press zoom 9, so it'll give me a good window. Oh, it looks like maybe I had some old data, or equations rather, typed into my calculator here. I apologize. Let me get those cleared out. We should not be seeing those running through my box and whisker plot at all here. All right. I will clear each of these out. We'll take a look at this. If you hit the trace button and kind of toggle left and right, it'll give you a sense of maybe how to label your x-axis. Okay. I'm just going to draw a rough sketch here. Keep in mind, these represent the DO levels, okay, the dissolved oxygen levels. Looks like something roughly at 2.87, and it spans all the way to the right at about 6.38. So I'm just going to count 1, 2, 3, 5, 6, 7 here, and then I'm going to move my cursor across. That'll give me a good sense of just roughly where to place sort of a 5-number summary here. Okay, our median is at 4.83. It's that part there. 5.5, and ends over here at 6.38. Okay, and so I'm just going to make the comment that it looks like there is no extreme skewness or outliers. Therefore, make sure you draw your conclusion here. Therefore, This is approximately normal, which means we can proceed with calculating the t-score and using like TCDF, or on this problem, we're going to use the calculator feature. The name of this test, this is a one sample t-test for means. Okay, now on the calculator, it is just called a t-test. But it is a good idea to say this is a one sample t-test for means. Okay, now we are to step T and O, which is where we're going to shift over, and we're going to do this on the calculator. Okay? So on the calculator, I'm going to back out of this. We're going to press Stat, go over to Test. We're going to come down and pick option number 2, t-test. Okay, now on this problem, I actually have the data, okay, each of the individual pieces of data from this sample. So I'm going to select data. I need to come down and fill in the value from the null hypothesis. That value was 5 milligrams per liter. So I'm going to make that a 5. Okay, make sure that you've identified the list where your data is located. That would be L1. And I need to change the sign on my alternative hypothesis to being a less than symbol. That's what we had drafted there. And we're going to come on down to calculate, press enter. We need to report a few things. We know in the T step, this is where we report what the t-score is, negative 0.94. Okay, in the O step, this is where we report the p-value. It would be excellent added communication if you went ahead and plotted where that t-score is, and since this was a less than problem, you shaded to the left of that. Okay, now the other thing that has to be written down is you have to write down that the degrees of freedom would be 14. If they took 15 samples at 15 different locations, this would be n minus 1. Okay, now that we have that, we can finish the problem up by saying that since the p-value of 0.1809 is greater than the alpha level of 0.05, we would fail to reject the null hypothesis. I'm not going to fill this in, we've done this so many times here. Our final conclusion would be then that we do not have convincing evidence that the true population mean DO levels in the stream or river is less than 5 milligrams per liter. Okay? Meaning it feels like maybe the aquatic life is not at risk. Okay? All right, hopefully that calculator feature is working out great for you. We're just going to, on this next problem, I filled in the majority of this just to kind of expedite this process because it does get lengthy, and after you've done so many of them, we kind of get the hang of sort of how this works here. But I just want to look at this last pineapple example because we're going to do a two-sided t-test here, and then I want to compare it to having done a confidence interval, and you can kind of see how you would arrive at the same conclusion. So this is talking about the Hawaii Pineapple Company. It says managers are interested in the sizes of the pineapples grown in the company's fields. Now last year, the mean weight of the pineapples that were harvested from one large field was 31 ounces. There's a new irrigation system that was installed in this field after the growing season, and managers are wondering whether this change will affect the mean weight of future pineapples grown in the field. It doesn't mention about whether it's going to make the pineapples larger or make them smaller. It just kind of says, is it going to affect them? So we want to keep that in mind when we're trying to think of what symbol we want to put as our alternative hypothesis. If there's not a distinct direction denoted here, we're probably going to be using a does not equal to symbol. It says to find out, they select a random sample of 50 pineapples from this year's crop. And then they give you some computer output here that we can see. Okay? So we're kind of given the stats here. We're not given the body of data from the sample. You can see right here, this is the X bar. This right here would be the sample standard deviation. Okay, what we need to fill in here is our parameter is going to be mu, the true mean weight of pineapples. Our null hypothesis would be that mu equals 31, whereas the alternative, we're going to say mu does not equal 31 ounces. And coming on down here for our conditions, that filled in that this was a random sample of 50 pineapples. We've got that this would be definitely less than or equal to all the pineapples grown, okay, for this particular field or company. Okay, and then the normality check here. Okay. Now, finally, one where we can use the central limit theorem. Since our sample size of 50 is greater than or equal to 30, we can use the central limit theorem to declare that this is approximately normal. We don't have to make a box and whisker plot and examine anything for extreme skewness or outliers. Okay, there we've got the name, the one sample t-test, and now we need to get the t-score and report the p-value. And so we're going to go ahead and use the calculator to do this. Okay, now I'm going to scroll back up so that we can see the data here. Okay, the information we're going to need to input is the mean from our sample and the standard deviation from our sample. Okay, so we are going to be pressing stat, bumping over again to the test menu, coming down and picking t-test. Okay, this time we have the stats, not the data, so you want to pick stats. Right? We had established our null hypothesis value was 31. We're going to fill in the sample mean, that's the 31.935, and the sample standard deviation is 2.394. Okay, I believe they had sampled 50 pineapples, and we want to make sure that we're picking the symbol does not equal to here. We're going to come on down and calculate, and we can record the t-score and the p-value. T-score and the p-value here. The t-score is 2.76, p-value 0.0081. If you remember, there's something else that needs to be reported, and it's not actually on our screen, so it's up to us to remember this. Degrees of freedom, 49. It's 49, not 4.3. Okay, I'm just going to add some really good communication here and show my t-score. Now remember, this was a two-sided test, so I need to put 2.76 and negative 2.76, and I'm actually shading left and right there. Okay. All right, now when you do a two-sided test and you're using the calculator, the p-value they give you has already been doubled, okay? So you're not going to double this p-value here. They've already combined both of those areas together for 0.0081. So we're saying since the p-value of 0.0081 is less than the alpha level of 0.05, we're going to reject the null hypothesis. And I'm going to highlight that because we're going to be looking at the confidence interval that's equivalent to this significance test. And I want to keep in mind here that our decision when we ran the SIG test was to reject the null hypothesis. So we're saying, look, we've got convincing evidence that the true mean weight of these pineapples, that it's not 31 ounces. That's what our alternative hypothesis said. It's not 31 ounces. Okay, now if we were to take the same data, and it's already in L1, and we wanted to run a confidence interval, and we're going to flip to this last page here. Now, I know this is already established here, but I'm going to walk you through here. Just running a confidence interval, it's showing you that this is the confidence interval that you would get. Here's what you would do on your calculator to run a confidence interval for this. Okay, you're going to go back to stat, test, and instead of picking t-test, you're going to pick, for me it's option 8, t-interval. Okay, again, we have the stats, and it's actually already all filled in here. I think this was asking you to do a 95% confidence interval. I'm going to go ahead and hit calculate here. And you can see that I come up with the exact same confidence interval that they have suggested here in the paper. Okay. Now remember how confidence intervals work. You say that we're 95% confident that the interval from 31.255 to 32.616 would capture, and that is going to capture the true mean weight of this year's pineapple crop. Now, let's look back at what we said with the SIG test. With this two-sided SIG test, we were trying to figure out, is the true mean weight 31 ounces, or is it something different than 31 ounces? And we were choosing at the end to reject that the true mean weight was 31 ounces. We were rejecting that. Now look at the confidence interval. Is 31 ounces a plausible value in the confidence interval that we had constructed? you can see that 31 is actually not included in that confidence interval. So our conclusion that we made from our significance test and the confidence interval that we have constructed both feel like they're in agreement with each other. The 31 is not a plausible value, hence we had rejected that null hypothesis from the SIG test. Okay, there's a few problems here for you to go ahead and try that's going to wrap up this section 9.3.